In this lecture, we'll talk about the transit method for detecting exoplanets. In the transit method, astronomers monitor the starlight of a star for periodic dimming, indicating that an exoplanet is blocking out a fraction of the starlight as it orbits. So we use the terms transit method or eclipse method equally. Until the launch of Kepler, most exoplanets had been found by the radial velocity method. This graph shows the phenomenal amount of data released just in the first year or so of the Kepler mission. As the exoplanet moves around the star, it periodically moves between us, the observers, and the star, blocking some of the starlight. Now notice that eclipse detection, or the transit method, is only applicable in a subset of the systems where the orbital plane is tilted towards us, so that we're looking in the equatorial plane. If we were looking straight down on the system from above, there would be no transit or eclipse. So this method is only possible for a small subset of the exoplanets, and astronomers have to make a correction for the missing data. Here's the detection of a single exoplanet transiting a sun-like star. Now we look in the equatorial plane where the transit can be seen as a short dip as it passes in front of the star. This happens for a small fraction of the orbit of the exoplanet. So many stars have to be observed at once to have a statistical chance of seeing this effect. But there's a problem with this method for typical systems, and let's use the solar system as an example. Let's use Jupiter and the Sun. Let's imagine we're observing the solar system from afar, hoping to detect Jupiter. Jupiter moves at 13 kilometers per second. If you were using the Doppler or radial velocity method, that's the Doppler shift you would have to detect Jupiter. But if Jupiter is considered to transit the Sun as viewed from the side, which it would do every 12 years, it takes less than a day to cross the Sun's surface as seen from afar. So in a 12-year orbit, that's about 1/500th of the time. You would have to watch closely. So you can see how difficult this technique is, because the transit occurs for a massive planet orbiting far from its star for such a tiny fraction of the orbital time. You will be spending most of your time watching the star, nothing would be happening, and then suddenly, for a tiny period of time, blink and you miss it, there's a transit and an eclipse. The solution astronomers use to this problem is not to look at single stars, but to look at as many stars as possible, so that on average, one of them or more of them are giving a transit in any period of time that you observe them. So the rare eclipses are essentially pulled in by getting good statistics and large number of simultaneous observations. And with the Kepler spacecraft, this was done by staring at one patch of sky where there were over 150,000 stars all being studied at once. Here's two examples are shown, orbiting sun-like stars. In one case, a small planet causes a relatively small dip or transit. In the other case, a larger planet causes a larger dip. The depth of the eclipse or the dip corresponds to the ratio of the surface areas of the planet relative to the parent star. So exoplanet size obviously relates to the eclipse. We imagine the planet is opaque, and so as it crosses the face of the star, it blocks some fractions of the star's light. And the ratio is very simple. It's the cross-sectional area of the planet divided by the cross-sectional area of the star. That's the fraction of the star's light that is occulted, and so the percentage of the star's light that is dimmed when the transit occurs. Smaller planets have smaller radii and therefore don't block as much starlight during their transit. In this animation, we add a detail to the transit method, where in addition to the exoplanet crossing the face of its star and causing a substantial dip, there's a second dip because the exoplanet shines in reflected light, and that reflected light goes away when it passes behind the star, causing a smaller secondary dip. These effects have now been seen in dozens of exoplanets by the Kepler spacecraft. What happens if a star has multiple planets? Here we have a top-down view, but when we're in the equatorial plane, there's the possibility of one or more of the planets to transit. They will transit with frequencies given by their orbital periods, and the light curve on the left will show the relative dips corresponding to the size of those exoplanets. In real data from the Kepler satellite, many instances of multiple planets have been found in this way. Here's data from the transit, and this is the kind of data that you get from the Kepler spacecraft showing real data. And here you see a transit observation where the dip is something over 1%, between 1 and 2%. Jupiter is 10 times smaller than the Sun, so if Jupiter crossed the face of the Sun, it would dim the Sun by 1%. So you can see right away that if this was a Sun-like star, the planet that's being seen transiting is slightly larger than Jupiter because the eclipse is slightly more than 1%. And you can see other examples here. You can see that the individual data from the CCD detectors is quite noisy, but because you're averaging over the time when there's no eclipse, the small region where there is an eclipse is still very easy to detect, and you can also model the data with a curve. Here are some real transit data sizes measured by the Kepler spacecraft. And initially, Kepler was finding far more Jupiter-sized exoplanets than Earth-like planets. And you can see the distributions here. The orbital periods. These are now, of course, Earth-sized planets on very short orbits, so they're hot planets, nothing like habitable. And these are Jupiter-sized planets also on short, rapid orbits, so they're hot Jupiters. So as we saw, hot Jupiters were the first exoplanets to be discovered. And just as hot Jupiters are easier to detect with the Doppler method because they have the largest masses and the shortest orbits, they're also the easiest to detect with the transit method. Because if you think about the geometry of a planet orbiting a star, when a planet of a given size is closer to the star, the odds of observing an eclipse are higher. And so it turned out that roughly 1 in 10 planets would transit their stars in the hot Jupiter scenario, as opposed to a tiny fraction of a percent of Earth-like planets crossing their star when you're looking for much smaller objects. So just as with the radial velocity technique, the transit method is strongly preferring to find hot Jupiters, and indeed that's what Kepler was finding early on. So just as with the radial velocity technique, the transit method is strongly preferring to find hot Jupiters, and indeed that's what Kepler was finding early on. The transit method has limitations too. Planets with a large radius produce obvious dips, easy to detect. You can see very strong detections here where the noise on the data is almost invisible and the transit is really clear. But as you get down towards super-Earth and Earth-sized planets, the data is much more noisy and it's much harder to detect that dip, which of course in the case of an Earth-like planet and a Sun-like star is 1/100th of a percent, 1 part in 10 to the 4. That's pretty subtle. Now the advantage is that you can take multiple observations because the orbit will repeat. And when you know the orbital period, you know when to add the data from the next time the transit occur, and you can add the eclipses together. In the case of Kepler, it was unwilling for the team to declare a detection of an exoplanet unless an eclipse was confirmed twice. In other words, a single measurement like this was not sufficient to declare the detection of an exoplanet. And even the repetition of that one more time was not sufficient. That would, of course, allow you to determine the period, but would not confirm the period until you saw it a third time. So Kepler used the third eclipse measurement of a given object to declare it to be real, and of course add the data together. Having had a third, if you had enough data, you could get a fourth, a fifth, and so on. And if you're talking about small orbital periods, in the mission of Kepler, you may have dozens or occasionally even hundreds of transits. But in the case of an Earth-like situation with a 1-year orbit, Kepler's mission wasn't long enough to find more than a couple of events. Planets at increasing orbital distances block less light from their star, and so it becomes increasingly difficult to detect transits as the planets are further from their star. Also, the transit geometry occurs for a very small set of orbital inclinations, and so it's just much rarer to detect, and you need to gather a lot more observations to find those rare instances. Let's get a sense of the amazing diversity of the exoplanets discovered by Kepler. Each little diagram here represents an orbit of an exoplanet around a sun-like star, or in many cases a dwarf star. The size of the dots represent the size of the exoplanets. The speed of the orbits, the speed of their orbits, obviously not to real time. You can see multi-planet systems in a number of cases. This is just a subset of the thousands of planets that have been found by the Kepler spacecraft. Some of the fastest orbits relative to the slowest orbits are fantastically fast, orbits of less than a day. The longest orbits, months or years. We'll zoom in on some of the most intensely speedy of these exoplanets. And the music, fittingly, is from Star Wars. To summarize this lecture, the transit method measures small dips in the light curves of stars to detect exoplanets. The exoplanet is crossing the face of the sun, blocking a small fraction of its light, leading to a dip in the brightness. And the size of the exoplanet is deduced using this method. Notice this method only gives the size but not the mass, whereas the radial velocity method gave the mass but not the size. So they're complementary in that sense. Exoplanet size limits the observation. For an Earth-like planet and a Sun-like star, the eclipse is 1/100%. And the Kepler satellite was designed to detect that, but not much less. And that becomes sort of the limit of the technique. Also, exoplanets at large orbital distances are hard to detect because a very small fraction of the orbital geometries give transits or eclipses.